Hey guys, so now we're lecture 32, and so for a quick review, for last lecture we looked at the differential mode gain, ADD, here, the common mode gain, ACC, and remember you can approximate this as being 0 if your output resistor is quite large, your output resistance. Common mode conversion gain, ACD, at 0. And also, this one is 0 as well, right here. If both sides are fully matched. We also looked at the differential mode output resistance. Differential mode input resistance, right here. Output resistance, common mode input resistance, and common mode input. No, wait, that's not the common. That's the common mode rejection ratio. I'm gonna fix that. It's right here. Okay, so on this lecture, we're gonna continue on with chapter 15. Oh wait, so before we do that, let me go over some things that you guys would need for your homework. So your homework will go a lot faster. So let's review these kinds of things right here. What is defined as a common source, common gate, common drain, common emitter, common base, common collector, and things that are just not useful. Okay, so here's the BJT and the FDT, right? So what we found out from a previous lecture was that the base and the gate are really good for inputs, and the collector and drain are good for outputs, and the emitter and the source can be either or. Okay? So keep that in mind, because we're going to go through a few of these circuits, and just keep this in mind how this goes. Okay? Because we'll go through and we'll look at which ones are either of these or which ones are not useful. Okay, and what we mean by not useful is if, for example, we try to assign an output for the base, right? Or we try to assign the drain as an input, then that would be something that's not useful. Okay, it doesn't mean you can't do it, but it just won't be useful. Okay, so base, gate, inputs, the collector and drain outputs, and the emitter and source can be either or. Okay, so for this one right here, here's a BJT right here. And let me ask you, which of these would you consider this as? This type of system? Now, of course, this is the AC equivalent, right? So the capacitors are not showing. And a lot of times, that's something you have to do. You actually have to put it in the AC equivalent form in order for you to easily identify which of these it is. Any guesses? Well, we know that the input's coming in where? The input's coming in right here at the base, right? So that's fine. So we know that it is useful, okay, because that was okay, right? And remember, this could be either or, that is like output. So we can scratch this one off, right? But which of these other 6 could it be? A common what? Emitter. Common emitter? You guys okay with that? It's okay, guess. Okay, so the answer is so common collector, okay, right here. And you can see that the collector right here is connected to the ground. Okay, so let's do another one. So, so what about this one right here? Well, first of all, is it useful? You know, so that's something you can think about. You know, is it useful? Right? You see the input right here. That's coming in to this part, and then you have the output right here. Right? Here's the gate. So do you think it's useful? No? Why do you think it's not useful?
It's not tied to base. The input, the input not feeding to base.
Well,
Or the gate.
that is true, but that's not the only one. Remember? So remember right here? Yeah, it is true. Having it go to the gate is good, but this right here, either or. Yeah, and that same thing right here. So, well, one way to look at it, the ones with the arrow, that's either or, right? Arrow, either or.
Right.
Both of these right here, the base and emitter,
Right.
coming in the top, those are our inputs, and the other one that's left is output. Maybe you can think of it like that. Okay, so that seems okay. So which of these is it?
Common gate.
Yeah, common gate. You see that? See the gate right here? And it's common to the input and output. Reference. Okay. Yeah, common gate. Okay, so how about this one right here? Is it useful?
Yes.
Correct, it is useful. The input's coming in to the base, right? And that's good. Here's the output. The output is right here, and that's fine for the output. And this can be either or. Okay, now it is useful. Now, which is it? Common emitter? Yes, common emitter. See that? So even though the ground is up here, it's all in reference to the input and output. So same thing. All these 3 points are connected. Here's another one. Okay. So first you want to ask yourself, is it useful?
Common source. That's useful.
So you think it's a common source and it is useful?
Yes.
Correct. Here's another one right here.
Common emitter.
And is it useful?
Yes.
Yes. Here's another one. Common collector. Is it useful?
Yes.
Yeah, that's coming into a base. Common collector. Here's another one. Now it's rotating now. Yeah, what about this one?
It's useful.
Common base. And you think it's useful?
Yeah.
Correct. How about this one? Common source. And it is useful, you think? Yep, that's going into the base. Common source. Okay. This one one right here. I guess a few more, okay. I'm going to get you to do this right here, the not useful ones. Huh?
Common gate.
Common gate? Is it useful?
Yeah.
Yeah. Okay, this one right here. Huh?
Common source?
You think it's common source? Is it useful?
I'm not sure. Yes.
Not sure?
Okay.
Yes, it is common source. It is useful. Here's another one right here. Common emitter, and is useful. Yep. Because that's output, that's input, and this could be either input or output. Okay, how about this one?
Common drain.
Common drain. And is it useful?
Yes.
Yep. Common drain. And this one right here, JFET. We haven't really dealt with these in this class, but have you guys had this in like your last class? Did you try JFETs?
I'm sure at some point.
Yeah. Okay. So, is it useful? Yeah, the input's coming in right here, right? So this one right here, common source, and it is useful.
So is that? Hang on. I don't remember JFETs.
Oh yeah.
I don't know who to talk about.
How do you know if it's a drain or a source?
Yeah. How does this JFET organize?
Yeah.
I got the error.
Yeah.
It's closest to, because you see that skew from the middle,
Yeah.
the log with the arrow. I think the side that's closest to is always the source. I feel like I remember.
Yeah. I think he's right. It's right here. And also, like here, this is the N channel. Here's a P channel, right here, right?
Yeah.
And it's similar. This is common source.
It's still close to the box.
Yeah, but it's your P channel, N channel depends on who's the majority carriers, right?
Yeah.
So what is that?
So is the arrow like?
Okay.
Oh, sorry. Can you go back? Can you go back? So would the arrow be like the gate, just where that is? Is this just the gate? All that-
Yeah, I believe so. On these right here, for the JFETs,
Yes.
that's correct. I think this is like the gate for those. Yeah.
Okay.
Yeah, but anyways, yeah. So we haven't touched on these this semester because we've been just concentrating on the MOSFETs and the BJTs. But yeah. So what about this one? You think it's not useful? Why?
So the gate does not have input, and neither does the emitter. So you're feeding the input to where your output should be.
Yeah. Look at that output. Look at this input. It's going in right here. And so we already know that only this could be input or that could be an input. I mean, well, this could be either or, right? So this is not useful. And it says here because the signal is injected into the drain. Okay, that's not useful. What about this one? This was the NMOS, here's a PMOS.
Still not-
Yes, same problem. And not useful. Okay, still going into the drain. What about this one? This is the last one, okay?
It's feeding the that's what's good. But as long as it feeds it, it's feeding the base or emitter. So it's common.
comes in the gate. Yeah. So remember the gate or the the base, right?
Yeah.
Or the gate, right? The gate and the base are only for the output. I mean, sorry, the other way around. The gate and base are only for inputs, right? This can be input or output, so that this is actually okay, putting that input right there. Yeah, so this one is not useful. Yeah, because the signal is going to the base.
So only because we're treating the base as the output, we turn the terminals.
Yeah. Okay, yeah, so this will make the homework hopefully a breeze now. Because circuits like that are in the homework. Okay. So, any questions about this kind of stuff? So if it appeared on the test, you guys be okay?
Like 50% of the test.
I know. Or all of it up. There's more than 12 of these questions.
Can this just be the practice test?
I know.
Right now.
This was the test you failed.
Yeah, but I think by like going through these, it started making more sense. Because remember, initially you guys were kind of unsure, like the first few, but then it started getting a little easier and easier as we went on, picking these things out. And yeah, so I agree. Okay, so let's move on with biasing with electronic current sources. Okay, so recall that that the Q point of the differential amplifier depends on the negative power supply, this negative VEE right here, and the DC common mode voltage VIC, and also that the common mode rejection ratio is limited by RE. So you can see that right here. So here's the VEEs in that equation, and that's and it shows its dependence right here for the Q point. VEE is also shown right here, and for the common mode rejection ratio, we have this RE. Okay, so those things right there are really important for the Q point, these two equations, and the common mode rejection ratio. Now, to remove those limitations, what you can do is bias the amplifier by using an electronic current source. This right here. Okay, here's one for the BJT. Here's one for the FET right here. Okay. Now, now if you do that, it stabilizes the operating point and it increases the effective value of RE. REE. So remember, REE was right here in its place. So we're going to replace that with this. And in fact, this current source has an effective resistance of REE. So we're not changing that around, okay? But it does do these couple of things like stabilize that Q point. And allows you to have some control over this REE. Okay, so this is sort of what it looks like. So if you did like an IV diagram, right? Here's current on this axis. Here's voltage on this axis right here. And here's the Q point of that, okay? So ISS, that's the current going through here. And that's the voltage right there. And the slope of this right here is the transconductance, or the conductance value of that, or RS1 over RSS. That's this value. So remember, this was RSS, this was REE. And it's the same thing. So this is just for the FET, but if you did it for the BJT, then this right here would be IEE, and this slope would be 1 over REE. Okay. So now if you're doing hand analysis, here's what you want to do. This element right here, which is sort of like a new type of element, you want to model this. If you're doing DC analysis, you model it as just a current source, which has some current ISS or current IE, right? If you're doing AC model, then what you want to do is put that back in terms of resistance. Okay, so that would be RSS if it's the FET model, or be REE if it's the BJT model. And inside of like a circuit simulator, it's modeled like this. So this type of model inside of a circuit looks like this, where you have this current source in parallel with a resistor, with that value resistor. Okay. Now, for this current source, can someone tell me, like, what is a current source can have a value of voltage that goes across it, right? And that voltage can drop like this, or it could be the other way around, where you have a lower voltage here and a higher voltage there. That is possible. Okay, but what is the resistance of a current source? What do you think a resistance is of a current source?
Would it be the voltage across it divided by the current that it's pushing?
That's if we're doing Thevenin.
Okay.
Yeah, that's if we're doing Thevenin. But this is like straight current source. No. That's zero? Zero. Yes, infinite. Yes. Yeah. Think of the resistance of a current source as being infinite. Okay. So think of this as being infinite. So if you're trying, think of it this way: if you're trying to send more current down this direction, the only current that would go here is just due to the current source. You can't increase the current or decrease the current on this branch. If you try to increase the current going in this direction, the only thing that would happen is it would go around this way. And then you would increase the voltage across here, right? But you would not affect the current over here. Okay. And also too, if you stop the current, then this current would still be going, except it would just go around in the loop. Okay. Okay. So DC analysis of the MOSFET differential amplifier. Okay, so MOSFETs provide a very high input resistance, and we've seen that before. And also we talked about this before too. They're often used as in differential amplifiers. Okay, so for a DC analysis, what we'll do, we'll replace this REE, or the RSS, with the current source ISS. Yeah, so that should be RSS to basic this. Okay, so this is the basic model, and then we'll just convert it to this. And the only thing that has changed is that this goes to this right here for our DC analysis. Okay, and another thing that can be useful sometimes is if you use a half circuit version. So basically, take this right here and we'll split it right down the middle. Okay, so if we split that down the middle, that's where this perforation is, right here. And now you have the current source, which is split like this. So this is like one half of it, and that's the other half.
Are we assuming that both half of the circuits are symmetrical in values? The RDs on both sides are equal?
Yes. Yeah, all this analysis, it is assuming that everything is equal. Both sides are totally symmetric and matched. Yeah. Wait, was that your question? Okay. So this is what we get over here. And so even though we're just looking at the left-hand side, this goes for the other side too. So whatever we figure out here, it applies to the other side. And since we're using DC analysis, we're taking this element and replacing it with a source. Okay? And so in this DC half circuit, the current in the source of the NMOS transistor is 1/2 the bias. So that's why this right here got replaced with this. Okay. And also the gate source voltage, this VGS, can be determined using this drain current expression right here. And we've seen this before. this right here. And so in solving this equation for VGS, the gate source voltage, we get this. And then we'll make the realization that this ID, the drain current right here, is going to be IS over 2. So just the IS goes here. And 2's canceled. Okay. And then last, since VS is going to be negative GS, okay, then the voltages at the MOSFET drains are this right here. So this voltage right here equals that one on both sides, right? These two things are equal. And that is equal to this VDD minus IDRD, okay? And so you're starting here, you have this current going through there, and so that's what this this voltage right here is equal to that voltage minus the voltage drop from here to here. Okay, and so the drain source voltages are this right here. So VDS equals that VDD minus ID RD plus your voltage for your gauge, your source. Okay, and so well that's it for today. But we'll take out from this point on Wednesday.
I was thinking for the third exam, could we do that on the Wednesday rather than Friday so that we could like possibly get it back on Friday, since that'll be the very last day of the semester.
Oh yeah, you want to make sure
Get
that
it back and look over
yeah,
it.
if you have to study for the final.
Yeah.
Okay, yeah, that's doable.
Okay, good.